let's start then. All right, so as promised, first proposition that we'll start after the break is the following. Suppose let G has an ideal, actually solvable ideal, such that G quotient by I is solvable, then G is solvable. Proof. Proof is two lines or one if you write small letters. Well, we have a natural projection, right? Pi from G to G quotient by I. So it's canonical projection. Right. So right, let me take so how to do this better? Let me see. Right, so let me take so this one is solvable, right? Therefore, there exists some so there exists some n such that dn of G over I equals to 0. Right. Then I claim that yes. So I claim that dn of G, so right. So let me move here. Then I claim that dn of G is inside I. Why is it like that? Because if I quotient by I, right, then this will live inside dn of G over I. But this one is 0. Well, this is not very correct way to write it down, right? So let me actually, since I introduced this pi, right, because I is not inside D and G, right? I would rather like to write pi of D and G. So this is because we have this. But then, since I is solvable too, right, then there exists some other integer, say k, such that dk of I is 0. So dk of y is 0 for some k. But dn plus k of g then lives inside dk of I. Right? So therefore, dn plus, well, let me just not use. So this is 0, and we are done, because there exists some integer n plus k such that the n plus kth element in the derived series is 0. Therefore, G is solvable. Yeah, by the way, what's written here is an easy but very useful property of a homomorphism of Lie algebras. That if I take a derived or lower series, apply a homomorphism of Lie algebras, it will live in the derived series of the image. You can prove it by induction, I guess. So that's where we use it. Right, because this is pi of g. Right, so pi of dn is inside dn of pi. What's written. Okay, so the most two important statements about nilpotent and solvable Lie algebras are Engel theorem and Lie theorem, respectively. Okay, so we introduced first solvable Lie algebras, so let us first go towards Lie theorem. And the most technical part of this theorem is the following lemma. So suppose that V is a complex, finite dimensional representation of a solvable Lie algebra G. So it means that we have a homomorphism, right, from G to GLV. So corresponding homomorphism. Then there exists some vector v inside this representation, which is a common eigenvector for all rho of x as x runs through G. So there exists a common eigenvector. That's the point. Okay, so the proof of this is rather technical. I don't want you to be overwhelmed with technical stuff right away. So maybe we'll leave it for the second part of the lecture, or I don't know, or just skip it. So let's see how much time do we have, right? Because I mean, it's kind of so the proof. Okay, so the proof will be after we talk about some other stuff. Proof later. So first, let's talk about consequences of this. You will be just too tired to understand everything else, okay? But I rather would like you to understand everything else rather than the proof of this. Or maybe not, depends on our abilities, but the danger is real. The consequence of this, number one, is that a solvable Lie algebra, the only irreducible finite dimensional representations of a solvable Lie algebras are one-dimensional. So corollary. All irreducible finite dimensional representations of solvable Lie algebra are one-dimensional. So why is that? How do you use this to deduce this corollary?
Because we can consider the orthonormal, the orthogonal completion. I'm not sure of the term of the vector space. The space that is orthogonal to V, and there is a representation induced on this vector space. Because.
But we don't even need this. It's easier because you don't need decomposable. You need just irreducible. Reducible means that you don't have invariant subspaces, right? But this thing is already an invariant subspace. Right? You don't even need orthogonal complement to that, right? So if you have just some representation, right? Suppose it's of dimension greater than 1, then of course, because of this lemma, has one-dimensional invariant subspace. So it's not irreducible. So the only irreducibles are one-dimensional. Yeah, so what you said is kind of, you're trying to think about indecomposable representations, right? Which are not direct sum of two, right? But there are indecomposable representations for solvable algebras of dimension greater than 1. And I think I will give you like a homework slash seminar problem that will cover that. Yeah, so proof. The vector V from the lemma is an invariant subspace. And that phrase kind of finishes the proof. Let's see some examples. For example, the most easy example of a solvable algebra is the abelian algebra, right? Abelian means the commutant of this algebra is 0. So it's D1 of this algebra is 0, so it stabilizes immediately at 0, right? But for abelian Lie algebra, so the center of this algebra is itself coincides with the algebra itself, right? But we know that the center of an algebra just acts by multiplying, acts on an irreducible representation, just multiplying it by a number, right? So therefore, if I take one vector, the whole algebra will just act on this vector by multiplication of a number. So it doesn't move this, right? So this is an invariant subspace. So for an abelian algebras, you know, for without this lemma, without anything, just to exemplify this, that all irreducible representations are one-dimensional representations. So examples. So abelian first, if G is abelian, then the center of G. So center means all x in G such that x commutes with y, right? For all y in G, right? So there, if G is abelian, then center of G coincides with G. And also you can deduce that an element of its center acts on a irreducible representation by multiplication by a number. And so therefore G, so every x from G acts on a V, where so this V is irreducible, and small v is an element of it, by multiplying on some number. Therefore, V is invariant subspace. Right? No element in X moves V anywhere else. Right? It just stays in itself. So it's invariant subspace. Okay. Another algebra is three-dimensional Heisenberg algebra. Three-dimensional Heisenberg algebra. I think we discussed it with somebody, or maybe like little bit on a lecture even. That's denoted like this. It has a basis, so it's spent on this, and bracket of x and y is z, and z commutes with everybody. So x z and y z is 0. So who is the center of the Heisenberg? Which? Yes, this one, this guy. So therefore, this one acts by some constant. Yeah, suppose that V is a reducible representation, is an irreducible representation of V, then Z acts on any vector from V by multiplying by some number. And this number is fixed for any V. It depends on, it depends on element of its center, of course. But in this case, we have up to multiplying by a constant is just the only one. Right. Then you do the following thing. You can compute, right. Right, so suppose your representation is finite dimensional, right? So finite dimensional. So then compute a trace of rho of Z over V. Right, this will be just lambda times dimension of V. On the other hand, this is trace of rho of x of a commutator, right? Rho of y. Because of this. But the trace of a commutator is 0, right? Because trace is cyclic respect to product. So this is 0, therefore in finite dimensional representation, lambda is 0. Right? So therefore in finite dimensional representation, this acts as an abelian algebra. Right? This thing acts as a 0 element, so the center just goes to 0. So this thing becomes like an in the image of under representation, homomorphism is just a abelian thing. Therefore, irreducible. We just reduced to the first case, right? Reducible should be one-dimensional as well. So this illustration of this corollary that follows from like a strong statement. But for this we didn't need this lemma yet. Yes, By the way, there is some infinite dimensional reducible representation. Which one?
The representation on the Fock space.
Okay, Fock space is what? No, I like this very much.
So we define the rising and the lowering operator with the help of let me think a minute. What? Okay, I know that they can define a lowering and a raising operator here, but I don't remember exactly what it looks like. Something like x plus iz or x minus 1 iz. I don't remember.
Yes.
Need a paper and a pen to derive. And then we can define the the eigenvectors of
right. You have a plus, a minus, a plus x by so your vectors have indexes, right? A plus raises index, a minus yes, your lowers the index, and z, I guess. So lowering and increasing operators you cook out of x and y, and this acts as multiplying by numbers, but different numbers.
This is the Casimir element of element.
Yes.
Yes. With the help of the other two, you build the reasonable and
yes. But this one is not faithful, though. So you have in Fock space, right? You have a vacuum, right? So you cannot depending on how you choose what is the Fock space. It's killed either by lowering operator or by raising operator, right?
Well, I'm not sure if this solves the problem, but you can define the Dirac's so the kind of Fock space which has an infinite number of eigenvalues of which has no true vacuum, like on which you need to define the physical vacuum as the action of all operators with negative indices on the quasi-vacuum.
Okay. So this one will be faithful, you mean? So faithful is such that this homomorphism in the morphism of this vector space has no kernel, right? So the Fock as it is itself does have some kernel because like a lowering operator is killed, for example, on a vacuum.
Easier version
yeah.
of this physics stuff is considered the space of polynomial.
Yes, that's what I was thinking.
And x is the operator of type x, and
yes.
y is derivative.
Yeah.
Z is
Yeah. Yeah, thank you very much. Yeah, this is very interesting to interact with physicists. So what I was thinking about is some polynomials in some variables. Yes. And then your x goes to, now we should, up to change of sign, right, is multiplication by u, y goes to derivative, and z just goes to 1. Maybe we should switch this too. So let's see. X, y, z, right? So is this true? So u d. No, I think it's the other way around, right? It's like that. So therefore, I should do like this. Right? Because if I take d and then differentiate u times some function, I u and then differentiate f plus I differentiate u, which is 1, and f is like this. So it's 1 times f. So therefore 1 is du minus ud. Like that. And therefore I have to send it like this. Okay, this is some fun detour. Let us move forward and now formulate Lee's theorem. Okay, theorem, so Lee theorem. So let again G be solvable, V finite dimensional complex representation as before. Then there is some basis in which each element of Gx as an upper triangular matrices. So that's the statement. Let's put it on board. So suppose that G is solvable, V is finite dimensional representation of G all right. Then there exists a basis of V such that well, rho of x, so the homomorphism corresponding to representation, is an upper triangular matrix such that for each x in G, rho of x in this basis is an upper triangular matrix. So the basis is the same for all elements in G, right? So there exists a basis, one basis for all elements, such that all these elements are mapped by the representation to upper triangular matrices. And let me remind, so rho is the corresponding homomorphism from G, right, to GLV. Let us prove it using the lemma. So the lemma was the most difficult part. This one follows immediately. Okay, so step of induction. Okay, let's find this vector which is given by this lemma that we stated before but never proved. So let V be the common eigenvector for row of x as x runs through G. It's an invariant subspace, subrepresentation, right? So therefore, I can quotient by this vector, by the subspace spent on this vector, and get another representation. So consider W, which is V quotient by C. Then dimension of W is dimension of V minus 1, right? Then by induction assumption, there exists some basis, a basis, W1, say dimension of V is n, then we have it n minus 1 of W, such that, let's say, rho corresponding to W of x upper triangular for every x in G. But then I can lift these vectors to V. Doesn't really matter how. So this are some like equivalence classes, if you wish, right? So take some representative for this class, and this each representative is a V, is in V. So let W1 tilde, W2 tilde, Wn minus 1 tilde be some lifts of W1, Wn minus 1 to V. Right? In the sense that right, the class of W tilde I is Wi. Then we are done, right? Because we already have a basis that makes our row of x upper triangular. So what is this basis?
This plus V.
Yes, but this basis should be ordered. Order matters. So where should I stick V? No, the last one. The first one. Because say W1 tilde, right? W1 tilde, when I lifted it, is W1, so W1, when I lifted W1 tilde, right? W1 tilde, it means that I added some multiple of V already, right? So, but for upper triangularity, so yeah, how to word it better? Right. Yes. So I have Right. So this is what I have. So I have W1, right? The thing that row W of x on my representation in upper triangular form, right, means that this can go into itself or to 0, right? So this thing sends this to some complex number times W1. And complex number can be 0, right? But W, so it means that row V right. So W1 then tilde is right. So then if I apply row V to this one, right, it will be C times W1 tilde because of this, plus something, some C prime times V, right? So this part kind of doesn't matter, right, when I lift. So I get this, right? So V should go first, right? So the conclusion is that then V, W1, W2, W3, so tildes here, and so on, is the basis or a basis such that row V of x is upper triangular for every x and g. So every time, right, so we have this, and, well, I don't know, maybe further explanations, you don't need them, right? So this is an example on W1. On W2, you have something times W1 plus something times W2. But when you lift it to this one, you have additional term like that, right? But since you inserted V in the first, the matrix that you get still will be upper triangular. That's it. All right. Next thing that I would like to, so this is Lee's theorem. It's not like it's applied in practice a lot, but it's applied in theoretical arguments and proofs a lot. So we will need it to prove further theorems. So that's why it's like a cornerstone in the Lie theory, in structured theory for Lie algebras. All right, is the following. Corollary. G is solvable if and only if the commutant of G is nilpotent. I think to prove this direction is easy. You don't even need Lie's theorem. So proof. So this one is nilpotent and hence solvable. So G, comma G is nilpotent, hence solvable. And quotient is abelian and solvable. So G quotient by this is abelian, and it means it's everything, nilpotent, solvable, and solvable. So we have an ideal which is solvable, quotient which is solvable, apply the first statement of the second part of today's lecture, and we get that G is solvable. So for that direction, we'll need Lie theorem. And we would like to apply it, so that direction is this way. We would like to apply Lie theorem to adjoint representation of G. Okay, does everybody remember what is adjoint representation? Yes, so an element X is sent to the bracket, right? So X is set to add X, which is a linear transformation of G itself, and add X acts on some other element of G as follows. So this is our rho. And V is G in this case. We apply Lie's theorem. It means that on our representation space on G, we have a basis such that add X acts as an upper triangular matrix. So let X 1 xn be the basis from Lie's theorem. Then in this basis, so actually we have a flag which is associated to this basis. So which flag? It's also sequence of subalgebras, if you wish, right? So you take F, this is a full flag since it is a basis. So V1, V2, and the last one is Vn, which is G itself, where Vi. So Vi here is right. x1, so the span of x1, xi. Then, because each row of x is upper triangular, then we actually know that at of G is inside B of F, right? So these are exactly upper triangular matrices. This is just informal as what I said. What not even I, but Lee, what is said. Right, so that these are matrices, and they are upper triangular in this basis. That's it. Then I would like to take add and apply to commutant. Then I would like to use that this map, adjoint representation, is a homomorphism of Lie algebras. Therefore, it is it sits at least inside the commutant of at G at G. But this thing, as we noted, is commutant of B of F and B of F. Well, inside, right? I should write inside. Right. But let me claim that this equals to n of f. I will not prove it right here, so I will let you prove it for the next seminar. All right? But it's, if you think just of upper triangular matrices, it's kind of clear, right? So if you commute to upper triangular, you get strictly upper triangular. The question is if every strictly upper triangular can be obtained as a commutator, or a sum of commutators. That's a little bit less clear, but I think you can do this, right? So this is homework. I will send it to you. But this thing is nilpotent. All right, and this thing is an ideal inside nilpotent, right? So therefore, at of G is nilpotent. Therefore, there exists some D. Okay, we are proving that this one is nilpotent, right? So let's see. We already get that the image of the adjoint map is nilpotent. So we have, first of all, since this one is nilpotent, what does it mean? It means that Dn of at g equals to, maybe n is not a good choice of letter here. Let us change to k. Is 0 for some k. No, I wrote that is definition of nilpotency. Now recall that what I said, that if, so let me maybe put it on board just to make it more clear. The property of homomorphism of Lie algebras. So lemma inside the proof, if phi is, so from G1 to G2 is a homomorphism of Lie algebras, then we have d I, doesn't really matter which index, upper or lower I take. I think it will be true in both cases. Well, if lower is true, then upper is for sure. Not really, but I mean, I think you should prove that separately for both cases. So di g1 is inside di phi of g. Yes. Is that true? Is it this way? So for each I, right? Yeah, this way. This is just because phi respects commutators. So that's a proof, basically, right? So therefore, if I move this d inside, this will be inside 0, kind of, right? So lemma is clear, right? If you wish, also if you don't understand it now, maybe on the fly, sometimes you cannot understand. Try to do it yourself. But the clue point, which explains everything, is that phi respects commutators, but di is all about commutators. That's it. Okay, so now apply this lemma to add. This is homomorphism of Lie algebras. It means that add of dk of g is 0 for the same k. Okay, but this means what is this thing? I take any y from G, right? And then start applying some. So what is an element of this thing? So again, we might think only about commutators, not about linear combinations, because everything is linear here, right? So suppose x is from here, right? How x is created? I take x1 and x2 commutator. This is this thing, right? Then I apply a commutator with x3. x3 lives inside GG, right? Just by definition. Then x4 also lives in here. And x5 and so on until xk, right? Or maybe not xk minus 1 or minus 2. You should correct me, right? So I think k minus, so this is 1, so k minus 2 maybe. So this is this thing. So that's how x looks like. So these two things are from G, and these things are all from G comma G commutator. Then I take this commutator with some y, any y from G, and I get 0. So the state, what I said here, is the same as saying, okay, let's take the bracket of this kind, like a huge bracket, where y is anything from G, x1 and x2 are anything from G, and x3, x4, everything up to xk minus 2, anything from G comma G. Then it's 0. But this is the same. So now, since I can take these three guys from G, I can take them as from commutant as well, right? So any bracket of such kind, right, where all elements are from commutant, is 0. This is exactly means that dk plus 1 of G comma G is 0. So this thing is nilpotent. So I kind of, so the point here is I know that this thing is nilpotent, but nilpotence is all about taking brackets. But this homomorphism is luckily also taking another bracket. So therefore we just kind of add plus 1 here, and we're done. So this is, what happened here, but accurately that's how you formulate it. Okay, very nice. So let's try to now to say something about nilpotent case. Something similar for nilpotent Lie algebras. Okay. So for nilpotent, can we say something? So what would be Lie theorem for nilpotent Lie algebras?
So it's strictly
Yeah. I mean, of course, you can just replace solvable by nilpotent there, because nilpotency means like implies solvability, right? But maybe we need something more, and we can say we would like to say in any representation you can find a basis such that nilpotent Lie algebra acts by strictly upper triangle measures. But this is not true, because there is very simple counterexample. Just take abelian Lie algebra, which is nilpotent, and just you can represent it by diagonal matrices, or just by scalar matrices, if you wish. Yes, and these are not strictly upper triangular. And there's no basis in this representation such to make them strictly upper triangular. So you should So the statement should be not exactly like that. There is some statement, and it goes like this. So theorem so sometimes this one is called Engel's theorem. Sometimes the corollary that I will state after that is called Engel theorem. Right. So here we need something more specific. So let V be finite dimensional complex vector space and G is a subalgebra of V of GLV, sorry, such that right. For every A from G, A to the power n is there exists. So every element in G is nilpotent. That's nilpotent in the sense of matrices, what you said to me before. So for every A in G there exists n such that A to the power n is 0. So suppose there is some subalgebra in GLV such that every element A in the subalgebra is nilpotent in the sense of matrices. Then there exists a basis in V such that yes, any element of G in this basis is strictly upper triangular. So this thing is proved similarly to Lee's theorem. And it has its own technical lemma, which maybe let me state it. So, but this lemma, since it is as much technical as to prove the lemma for Lee's theorem, but even a little bit more complicated. This one we will not discuss. I mean, we'll lose a lot of energy, but never learn anything. So, you know, it's your usual abstract algebra proof. You just, you know, do something with a lot of arguments, make a lot of steps, and voila, at some point you got the proof, but never understood anything. So anyways, So the theorem follows from the following lemma, from the lemma. Suppose G is like, so suppose G is like in theorem, in Engel theorem, then there exists vector V in V such that, so for Lie theorem, we had that this vector was common eigenvector. In this case, it is the vector which is killed by all the elements. So X acting on V is 0 for every X in G. So proved similarly to lemma for Lie's theorem. All right. So the lemma for Lie's theorem we are yet to prove. Let's see. So there is corollary for this theorem, which is sometimes called also Engel's theorem. So depending on book which you read, we will call both of them Engel theorem. Maybe the corollary we'll call second Engel theorem, just to
You can call the first theorem the Marx and this theorem on the second.
Marx Engels theorem. Yeah.
And that's easy.
And the second one is Lenin Marx Engels theorem. Yeah, fortunately it's not Engels, so that's why I sometimes just say Engel theorem, okay? Corollary. Second Engel theorem. So you see in this theorem, it doesn't say anything about nilpotent Lie algebras though, right? Just some algebra with nilpotent elements inside, a GOV. So this one is about nilpotent Lie algebras. So it says that Lie algebra G is nilpotent if and only if add X is nilpotent for every X in G. So let's prove this one using the first Engel theorem. Right, so this way is clear, right? Just because of definition, right? So this way I don't know. So if G is nilpotent, it means that dn G is 0 for some g, for some n, and it means that at x to the power n plus 1 maybe is 0. Even n is 0. And we are done. The other direction, we need to apply Engel theorem to. So we have G, and we have its image under the adjoint representation. So this lives inside GL of G, or linear transformation of G itself, right? And it satisfies the properties in Engel theorem. Why? Because, well, that's our assumption, right? So we assume what is happening on this side. Add x is nilpotent, right? And add x is exactly an element in this subalgebra, right? So this is exactly what's going on in this Engel theorem. So satisfies conditions of first Engel theorem Therefore, there's a basis in G, right? Such that in this basis, each element of this thing is upper triangular. Right, we are proving that G is nilpotent, even strictly upper triangular. Right, so there exists a basis x1 again, x n. I don't know. Did we use n? Yes, we did. So I don't know. K basis of G such that at G acts by strictly upper triangular matrices therefore, we already discussed that it means that add G is inside n of f. Yeah, so maybe I don't even need this. So they're all strictly upper triangular matrices, right? So once you start commuting upper triangular matrices, right? At some point, they just become so add G is in n of f, right? Right. So I'm proving that G is nilpotent, right? How to do it in a short way. I don't need any flex, sorry. So I'm starting to kind of switch off to towards the second hour. So I really need a flag, right? But not for n of f. So I actually let me form this. So let gi be span of x1, x2, xi. So I claim that I have a sequence of ideals, actually, right? Because of upper triangularity, if I commute gi with something, it will be in gi itself. Actually, it goes to gi plus 1. Gi minus. Well, so here it's kind of we need indices. So g0. So maybe I would like to call this one gn minus I. Gk minus I, right? Just to make things match what we did on the first lecture. Then g0 is g itself, right? Then inside I have g1, and then g2, and so on. And gk is just 0, right? So all these things are ideals, all right? And right, for solvability, I also claim so that they satisfy this criterion of nilpotency, right? I claim that G with GI is inside of G I plus 1. You're thinking maybe I should put plus 1 here? No, I think it's okay. Yeah. So this is true because the basis of that I chose. I chose such a basis that's strictly upper. The add is strictly upper triangular. Therefore, I end up in subspace with index which is strictly bigger, right, in the smaller subspace, right? So this is because matrices G matrices at X are strictly upper triangular. But this is a condition for G to be nilpotent, right? So therefore G is nilpotent. And we are done. Okay, yeah, so next week we don't meet, so we will have more time to solve problems, but we covered kind of more material today, so it's all fair. Okay, thank you.